So we're back for this last part of 5.2. So now we have an understanding of the ways we can find probabilities for a binomial probability distribution. We're now going to apply those and try to find some means and standard deviations. Now you're probably saying, oh no, more formulas. Well, these formulas are going to be much, much nicer to work with. Now for a general probability distribution, this is our formula. We have the summation, we had to find the product of x times p of x and then add up that column. A lot of work. For binomial, it's much, much quicker. All we have to do is multiply n times p. So if it's binomial, much, much nicer to work with. Standard deviation, again, we got this long, complicated formula. For binomial situations, it's just the square root of n times p times q. Whoops, very, very quick. Sorry about that. Okay, so now that we know how to find means and standard deviations, we can then apply this range rule of thumb so we can look at significant values. So remember, we can look at them in terms of probabilities, but we also like the range rule of thumb. It's more concrete. It's one of three buckets. So it's either less than the lower cutoff, it's greater than the upper cutoff, or it's between the two cutoffs. And if it's between, then it's not significant. All right, so let's try a few. Assume that a procedure yields a binomial distribution, yay, with n trials and the probability of success for one trial is p. Use the given values to find the mean and standard deviation. Also use the range rule of thumb to find the min significant value and the max significant value. All number crunching. This is all number crunching. So if we want to first find the mean and standard deviation, so we know we got to multiply our n times our p. And we can do that pretty quickly. So let's just double check on the calculator. I think it's 375, but it is. So 3.75. Now remember, with means and standard deviations and even the min and max significant values, we're going to need units. Now in this case, we lucked out. There's no units on anything. So we don't know what we're really talking about, so we don't need units on this problem. Standard deviation, we need the square root of n times p times q. Oh my God, they didn't give us q. What are we going to do? Well, we can find that, right? 75% for p, which means 25% for q. So now we can keep going. All right. So 5 times 0.75 times 0.25 equals that. Now we got to square root it. So 0.96824. And so what should we round it to? Well, remember, use your mean as a guide. If you're going to go two places with your mean up here, more than likely you want to go two places with your standard deviation. Minimally. You can go more, but minimally you want to go the same amount. So 0.97. All right, and now we can do our min significant, which is going to be the mean minus 2 standard deviations. So that should give us 3.75 minus 2 times 0.97, 1.81. So now we need to add 2 standard deviations. So 3.75 plus 2 times 0.97 equals 5.69. Done. Easy peasy. All right, now the questions are going to get a little bit more wordy and a little bit more, tricky, obviously. That one was nice because they just said, here's n, here's p, go. Well, so for the next one, random guesses are made for 50 SAT questions, multiple choice questions. So n is equal to 50 and p is 0.2. All right, so now they're giving us a little bit more context. So the mean in this case, 50 times 0.2, which better be 10. So random guesses on questions. So 10 questions, and I'll put in parentheses, correct. Because that's the thing, you're trying to guess right, hopefully, not guess wrong. So there's a 20% chance you're going to guess right if there's 5 answers. Okay, standard deviation. So you have 50 times 0.2 times. Now again, I'm not writing the Q up here, but a lot of these you can do pretty much in your head, hopefully, but definitely use your calculator if you're not 100% sure. So 0.8. So in this case, well, we're going to have the square root of, well, this was 10, remember. 10 times 0.8 is 8. Square root of 8 is 2.828, and so on. Now here's a dilemma though. We got no decimal points on our mean, and we got a ton of decimal points on our standard deviation. So how many decimal points should we use? 2, 3, 1? Well, remember, your data is always discrete in this case. So it's all countable whole numbers. So I would say minimum you need is 1. If you wanted to go 2, that's fine. But minimally, you'd have to have 1. So 2.8 questions. And so if we do our min, now I don't like to just write min because sometimes that gets confused with the 5 number summary. So just putting min sig just kind of helps clarify that it's the minimum significant value, not the minimum value in the data set. So 10 minus 2 times 2.8, so that's 5.6, so this better be 4.4. And then your max sig, 10 plus 2 times 2.8, which better be 15.6. Now, I'm going through the motions here, you're going through the motions, but you're not really analyzing this, I'm sure. What is this really telling you, though? You know, if we're dealing with a 50-question multiple choice test and you just flat out guessed, there's a average chance that you'll get 10 questions right on the average just by guessing. That's it. Standard deviation is 2.8. So your range rule of thumb says that we would expect anywhere between people getting 5 questions right to about 15 questions right. If we got in that range, that would be not unusual, and that would be typical. But as soon as somebody gets more than that right, if they got 16 questions right or 17 questions right, we then start to question that because that's above what we would normally expect. Same thing on the low side. If people got 4 questions right or only 3 questions right on this 50-question test, we would again scratch our head and say, that's a little bit low. I mean, you'd have to do really bad guessing to get that low. So that's the way you have to kind of frame these questions once you get this information. You know, so hopefully that makes sense to you. But if it doesn't, let me know. Let's try a few more. All right, drug test. Whoops, helps if you can see it. Drug test. In an analysis of the one-panel THC test for marijuana usage, 300 subjects are tested, and the probability of a positive result is 0.48. So what's our information we need to get the ball rolling? Well, 300 subjects, that's going to have to be our N, right? Positive test result, so there's our P. And so we also know our Q, 1 minus that better be 0.52. So there's our information. So now we can find all of our parameters. So we got 300 times 0.48, which is 144. So what would the units be for this? So 300 subjects. So 144 subjects. And now, again, if you want to be even more clear, what about those 144 subjects? 144 subjects would have a positive result. So I'll just put pos next to it. So that's what we would expect in this situation. 144 would be positive if it's 48% success rate. Standard deviation so we get our N, our P, and our Q, and let's just do that on the calculator. So we already know what N times P is, so 144 times 0.52 equals that, and then we need to square root it. So 8.6533, and it keeps going. So same question, what should we round it to? Well, no decimal points. Let's go 1. 8.7. So 8.7 subjects. All right, so now we can get our min and max. Now, I'm just looking at the previous page, and I did remember the units, so I hate it when I forget the units. So let's make sure we don't forget them on this one as well. We got our min significant. So we got our 144 minus 2 times 8.7. Well, let's see, 8.7 times 2, that looks like 17.4. 17.4 from that. I better do it on the calculator just to be safe. I hate it when I can't think. 2 times 8.7 equals, there it is, 126.6 subjects. And then our max. So now we got to add. So 144 plus 2 times 8.7 equals 161.4. All right, I think we got a pretty good start on this. So you can kind of see the pattern. The last couple of examples we're going to see, I'll do in the next video, but they're going to be a little bit more involved, and they're going to try to tie in some of the stuff we've seen back from the beginning. So stay tuned for that.